Much of modern trade and industry is dependent on a prosperous and efficient shipping industry. In recent years, this improved efficiency has been accompanied by greater attention to safety and environmental responsibility. But while pollution regulations have been tightened and more strictly enforced, another very serious problem has become evident: ballast water. In some circumstances, ballast water can carry diseases, microscopic organisms and sea creatures from one part of the world to another. This may also have led to the spread of deadly human pathogens like typhoid and cholera. So ballast water management programs are being introduced to try to prevent the spread of aquatic nuisance species. In this video and accompanying booklet, we will look at how ballast water can be managed at present and note the safety issues that must be addressed to ensure ship stability. Unlike garbage or oil, ballast water is not an obvious pollutant. Any contamination is not easily visible. So why should it have such a harmful impact on the environment? The problem arises from the huge quantity of ballast water moved around the world. In US coastal waters alone, vessels discharge over 57 million metric tons of ballast water each year. Even if only a fraction contains foreign aquatic species, it still adds up to an enormous number of organisms. And whilst other pollutants, even a major oil slick, can be cleaned up, once established, it is virtually impossible to get rid of an aquatic nuisance species. An ecosystem is the interaction between all the animals and plants that are local to that area and their environment. To remain viable, each ecosystem must maintain a natural balance between the competing species. If this balance is disturbed, then the results can be devastating. With so much concern about the environment, it has opened up an international debate.
Ballast water as a problem has only been identified probably in the last 10 years. Our objective at IMO is to introduce international regulations so that there is one set of rules which will apply throughout the world. The regulations are still being developed, but I would expect that all ships that are travelling on international voyages, and I mean long-distance voyages rather than short voyages between, say, Dover and Calais, or perhaps between Korea and Japan, but ships on longer voyages globally will all be required above a certain tonnage to have a ballast water management plan, so that if they do come into an area of the world or zone, region where there are ballast water management requirements, then they will be able to comply. They'll have a plan which will tell them what they can do and what they can't do.
The Great Lakes of North America. 5 inland lakes that make up the largest area of fresh water in the world. Connected by a series of waterways to the Atlantic Ocean, it is the industrial and agricultural heartland of the USA and Canada. In 1986, it is thought that the discharge of ballast water in Lake St. Clair, near Detroit, introduced a tiny shellfish into that ecosystem. Dreissena polymorpha, the zebra mussel, is a native of Europe. Within the space of only a few years, they were to have an enormous impact. With few natural predators, zebra mussels have changed the biological balance in the area. They now threaten both the local shellfish and the commercial freshwater fisheries. Zebra mussels build colonies on any available hard surface. Massive numbers of these shellfish group together. And if their chosen site is a water intake for a power station, they will soon block it entirely. With as many as 700,000 zebra mussels packed into each square metre, totally removing them has proved impossible, and their control has so far cost more than $5 billion. On the other side of the world, Tasmania is an island state of Australia with its own unique ecosystem. But in recent years, the Tasmanian oyster industry has been put at risk by the arrival of the northern Pacific sea star, Asterias amurensis, which has an insatiable appetite for the native bivalves, and by the much more serious threat of toxic dinoflagellate algae. Dinoflagellates, usually visible as a red tide when the build-up is severe, cause various forms of shellfish poisoning, which also pose a major health risk to humans. In Australia and New Zealand alone, production worth tens of millions of dollars has been lost, and many people have died. The Black Sea was once home to a thriving fishing industry that is now in serious decline. Pollution is a major factor, but it was the accidental introduction of the comb jelly, a kind of jellyfish, that all but closed down the local fisheries. From its arrival in the mid-1980s, the comb jelly population rose dramatically. Within a short space of time, the comb jelly became a major contributor to the decline of the anchovy catch. From 650,000 tons a decade ago, there is a mere 15,000 tons caught today. Without a fishing industry, boats are laid up, and the region now has severe unemployment. The experiences of the Great Lakes, Tasmania, and the Black Sea show that if a species arrives and becomes established where it has no natural predators, then chaos ensues.
The economic costs of aquatic nuisance species are clearly in the billions of dollars, and the key thing that makes aquatic nuisance species quite different from other nuisance species is that it is, once they've established, it is almost virtually impossible to overcome the problem, to manage the problem, certainly to totally eliminate the risk, and that establishes them as quite different from any of our well-known terrestrial pests. My country, and indeed many others, think that we all have an obligation to the future, and therefore that we need to act in a responsible manner, that we are protectors of the environment and should take whatever action is necessary in that regard. We now know enough about the ballast water problem to be able to do that. We have a particular affinity with the sea, both in my country and in many other countries, and therefore we think that it's essential that we protect the marine environment. That's what ballast water management is all about.
Ballast water is an essential part of vessel safety, helping to keep the vessel trim and stable and the propeller underwater when the ship is not loaded. When taking on cargo in port, the usual practice for most ships has been simply to discharge ballast water that may have been loaded on the other side of the world. But because this may introduce unwanted marine life, in some areas, the practice is no longer acceptable. The solution is to handle the ballast water in accordance with the Ballast Water Management Plan, which should follow the IMO guidelines on this subject. The Ballast Water Management Plan is individually tailored to each vessel and at present relies mostly on mid-ocean ballast water exchange. Exchanging ballast water at sea must always be undertaken with extreme caution. The master will only authorize it if the conditions at sea allow it to be completed safely. The specific methods will vary from ship to ship and will be laid down in the vessel's operational procedures. There are two main methods of ballast water exchange: sequential and flow-through. The sequential method requires that each ballast tank is emptied and then refilled. To maintain stability, tanks are usually paired, port and starboard. Even so, because each discharge represents the removal of an enormous weight, it can induce dynamic strains in the ship's structure. The flow-through method relies on overfilling the tanks by pumping in more water and letting the original contents flow out. To flush a tank thoroughly, 3 times the volume must be pumped in to remove 95% of old ballast water. Some vessels will use a combination of these methods, depending on the prevailing conditions. The exact procedures will vary from ship to ship. Following the Ballast Water Management Plan will minimize the risks. Exchanging ballast water at sea can affect the trim and draft. The engine intakes may come out of the water. It can set up stresses in the hull, leading to structural failure. And, potentially, it could cause a loss of stability. Even in calm weather, you must carry out this procedure with extreme caution. Under no circumstances is it ever worth the risk to speed up the process or take a shortcut. Such action could result in the vessel breaking up and sinking. The safe exchange of ballast water at sea requires that it is carried out well within the limits of the vessel's trim and stability data.
Just to remind you, the hazards to be found walking around the main
The crew must understand what they are doing. Everyone involved in ballast water exchange should be thoroughly trained and properly briefed about their responsibilities. And contingency plans should have been prepared in the event of an emergency, such as a sudden worsening of the weather or equipment failure. Exchanging ballast water in the middle of the ocean is an effective stopgap technique that will reduce the risk of foreign marine life invading distant shores. But it is by no means the best long-term solution. Governments, universities and marine research establishments throughout the world are looking at alternative treatments. The problem with all ballast water is to find a way to sterilize it and kill any organisms that are contained within. Fine filters fitted to the ballast pumps can significantly reduce the intake of exotic organisms. To be effective, the filters must have a small pore size. The drawback here is that they would quickly clog up unless they had a very large surface area. Adding a recirculating treatment system may make it more viable. Current research suggests that a wedge wire strainer is the most technically feasible system available. Until recently, using heat to treat ballast water was not thought to be commercially viable. In 1997, the Australian Quarantine and Inspection Service, as part of their Strategic Ballast Water Research Programme, modified the bulk carrier Iron Whyalla. The vessel uses the main engine to heat the ballast water to a temperature of around 40 degrees Celsius. After 2 minutes, this effectively kills nearly all marine life. However, some human pathogens, cholera for example, can survive this treatment. This technique is only practical on long-haul voyages and generally would not be feasible on much shorter journeys. Other researchers are experimenting with ultraviolet light, ultrasonics, oxygen deprivation, and chemical treatments. One of the most recent developments exploits natural toxins. Based on quinones from the black walnut, a small dose will kill the microscopic sea creatures in ballast water. After a short period, it breaks down and can be safely flushed with no further environmental risk. Some countries have already passed laws, and the International Maritime Organization is preparing globally acceptable regulations covering ballast water. Practical ballast water management requires 2 elements: a ballast water handling plan and accurate and up-to-date records. The ballast water handling plan should be prepared in advance for every voyage. This level of pre-planning is essential for the safety of the ship and its crew. Because there is a lack of agreed international standards and few harmonized rules, the plan will consider factors as diverse as the specific requirements of each port state control and the likely weather conditions. It will also provide contingencies so that the vessel can complete its voyage with as little disruption as possible. Record keeping is ultimately the responsibility of the master. Usually, he will appoint a nominated ballast water management officer. They not only ensure that ballast water treatment and exchange follows the overall ballast water management plan, they must also maintain the ballast water handling logbook and keep past records available for inspection. The layout may vary from company to company, but all will require similar information to be kept. The main form, the ballast water reporting form, is a record of loading and discharging of ballast, both in port and exchanged at sea. Part 1 lists information about the vessel: name, type, IMO number, owner, and gross tonnage. Part 2 shows the total ballast water on board and the total ballast water capacity. Part 3 specifies the number of ballast tanks on board, how many are in ballast, and the number of tanks exchanged. Part 4 is a detailed history of the ballast water. It includes the tank type, the date, port or the exact latitude and longitude, the volume, the water temperature at the time of the uptake. For exchange, the sea height, and at discharge, the salinity of the ballast water. This information is a legal requirement in a growing number of countries. With the availability of new methods, some nations are introducing ways to check that the ballast water uptake and discharges recorded in the log are indeed correct.
The importance of the records and data as to how a vessel's managing its ballast water is very important to the regulatory authorities. Port State Control officers, when they come on board, can review this information, get an idea as to what the vessel's ballast water management practices have been, to verify whether or not a exchange has been conducted. And we also are using this information to develop future legislation, regulations, and to develop our ballast water management program within our country. So the more accurate the information is that the master provides and is able to make available to us, the better decisions we should be able to make in the future concerning what regulations and what steps are needed to address ballast water management.
Failure to comply may lead to penalties and loss of revenue for the shipping company. The vessel may be required to retain her ballast and load less cargo. The ship may not be allowed to dock. She may be forced to go out to sea and exchange her ballast water. And there is always the risk of a heavy fine or even imprisonment. To avoid such penalties, and to prevent the unforeseen ecological and economic catastrophes that can occur from the introduction of harmful species into new environments, ballast water management will become a widely used procedure for seagoing vessels of all kinds. Its safe management will be an essential part of good ship operation.